Now that we've discussed what a polynomial function is, let's spend some time finding the zeros of a polynomial function and also finding polynomial functions given certain zeros. And this will all help build an understanding of how we can finally actually start graphing polynomial functions. So let's start with this first example here. I'm giving certain conditions in these problems, and it's up to us to come up with a polynomial functions that satisfy these conditions, making sure that we are going to have integer coefficients. And important to note here that there are more than one solution, or more than one function, I should say, in each of these problems. There are technically an infinite number of them that you can come up with, but I'm just going to go with the one that I think is the most straightforward. So let's start with this first one. So in this first problem here, you're given the conditions of a degree of 3 and a 0, and the following zeros. So we know that for every 0, we can say x minus that 0. So if we say, for example, that x is equal to some 0, which we'll call a, we know that x minus a has to be a factor. So with that in mind, we can then start writing our function using function notation as x minus negative 1/2. And now here we have x minus 3, and we have also x minus 3 as well. Now let's clean this up a little bit. We could leave it as it is, but a couple things. One, we want to have our function in general form, and we want to make sure that we have integer coefficients. So something that we can do here is we can introduce a vertical stretch. In other words, we can actually multiply this function by the denominator here. So this would become x plus 1/2. And if I want to negate this fraction here, I could just multiply everything by positive 2. So what that'll become, let me just clean this up here, is the following. We can say, and let me just write this as x minus 3 times x minus 3. So this then would become 2x plus 1. And this is just x minus 3 squared. You can write it like that, or you can write x minus 3, x minus 3. We're going to have to multiply it all together in just a moment. But we can see here what this does is this prevents us from having any fractional coefficients. And this allows us to also multiply this a little bit more easily. Now, if I'm multiplying this all out, let me just go ahead and just do this work here on the side, just in another color. This is kind of like scratch work. You wouldn't have to show this, but x minus 3 squared is x squared minus 6x plus 9. And I'm going to multiply it by 2x plus 1. And in the same way that you would do multiple digit multiplication, that's exactly what I'm going to do here. I'm just going to do 9 times 1, which is 9. I'm going to go 1 times negative 6x. That's negative 6x. 1 times x squared. That's going to give me x squared. And now I'm going to do the same thing to the next column. So 2x times 9 is 18x. And since this is going to be right here, I'm going to place this underneath the negative 6x to align it with the common terms. 2x times negative 6x is negative 12x squared. 2x times x squared is going to be 2x cubed. And so I'm going to add all of this up. So I've got 9, 12x, negative 11x squared, this was positive, 2x cubed. So I can then put all of that together by saying my function, f of x, is equal to 2x cubed minus 11x squared plus 12x plus 9. Okay, and I'm just a bit of a visual learner, so that just helps me see everything just kind of vertically lined up nice and easily. All right, so there's our function that has the following zeros with a degree of 3. 3 zeros, degree of 3, that all seems to line up pretty well. Okay, now let's try this next one here. Now in this problem, you'll notice that we've got 3 zeros, a degree of 3, so I can then start saying the following. F of x is equal to x minus 3, x minus my entire 0, so 2 plus root 11, and then x minus my other 0, 2 minus root 11. Now, there are a couple ways to do this, but you can see that this part right here, to start multiplying this out and putting this in general form, could get a little tricky. So something that I like to do is the following. First, I'm bring down to x minus 3. I'm going to go ahead and distribute that negative. So I'm going to write this as x minus 2 minus root 11. And then this is x minus 2 plus root 11. Now, I'm going to actually group together these x minus 2's. And pause and ask yourself why you think I'm doing this. And hopefully you're seeing the structure here, that this is a minus 5 times a plus 5. Do you remember what this becomes? This is a difference of squares, right? And so what's nice about this is I can then, let me just go back to my original color. What's nice about this is I don't really have to multiply all this out. I can just say the following. X minus 2 times x minus 2 squared. So let me write that here. X minus 2 squared. That's my, again, a squared. And then I also have, let's go back to my original color. I also have negative root 11 times positive root 11. Well, that's just b squared, so that's minus 11. That's my b squared. So I still got to do some multiplying, but this is way easier than having to try to multiply a bunch of radicals and adding a bunch of radicals together. So let's just clean this up. This is x minus 3 times, let's expand this out, x squared minus 4x. That's plus 4 minus 11, so that's minus 7. And then, again, it's up to you how you want to multiply this out. I can say x cubed minus 4x squared minus 7x. And underneath, I can say negative 3x squared plus 12x plus 21. If I add all this up, I get x cubed minus 7x squared plus 5x plus 21. And here is my function in general form that satisfies the conditions of having these zeros and a degree of 3. Okay. Now let's do something a little bit different for this next one. For this next one over here, I'm gonna introduce something. I want to ask that this function, I'm going to state a condition here, that this function goes through negative 36 when x is equal to 1. In other words, that the point 1, negative 36 must lie on this graph. Well, what am I doing right now? What I'm effectively doing is I am ensuring that my function, and keep in mind with all these previous problems, there could have been an infinite number of solutions because I could have introduced an infinite number of types of vertical stretches or shrinks. By giving this condition here, I'm ensuring that I want to find the function that goes through this exact point. So I'm going to set it up the same way. I'm going to say, all right, we got x minus negative 2 or x plus 2. It's telling me it's got a multiplicity of 2, so that means I can square this. And I also have x plus 1. Now, because it's also telling me that I've got to go through the point 1, negative 36, I'm trying to figure out what is my vertical stretch here. So I want to find out what is my vertical stretch or shrink, possibly, that ensures that this function will go through the point 1, negative 36. Now, you can expand this out and write it in general form first. It's up to you. You could also just now solve for a while it's still in factored form. So I'm going to plug in these points. I'm going to say negative 36 is my y value. This is my x, this is my y. So negative 36 is my y value. I'm still solving for a. Now I'm going to plug in positive 1. That's 1 plus 2 squared times 1 plus 1. So negative 36 is equal to a times, let's see, that's 3 squared, that's 9 times 2, that's 18. So we know that a must be equal to negative 2. Now that we know that, we can start writing the function as negative 2 times this original function that we had before we found out the vertical stretch. So it's negative 2 times x plus 2 squared times x plus 1. Well, let's go ahead and put that in general form. X squared plus 4x plus 4 times x plus 1. And for the sake of time, I'll just jump straight to my general form. And there is my function. Introduce not only a vertical stretch, but also a reflection to ensure that my function will go through the point 1, negative 36. Okay? All right. So now that we've talked a bit about how to find polynomial functions with these given zeros, now let's look at how would we actually sketch polynomial functions. And an important thing to know before we actually sketch polynomial functions is the following. We've got to talk about what the multiplicity of a zero does. And important thing, and the easiest way to describe this is if your multiplicity of your zero is odd, then your graph is going to cross the x-axis at that particular x-intercept. If your multiplicity of your zero is actually even, then the graph we say is tangent to the x-axis at that x-intercept, or more simply, we can just say that it quote-unquote bounces off. It's going to bounce off the x-axis at that point, okay? And one more thing that we should know, and I just drew this ahead of time, but when your polynomial function has a degree of n, that tells you that at most you're going to have n minus 1 extrema, or turns, if you will. So remember, extrema refers to a relative minimum or a relative maximum. If your degree is 4, that means you could have possibly 3 relative extrema or 1 relative extrema. So what about when your degree is something like 5? If your degree were 5, for example, then you could have something that looks like this. You could have something that looks like this, or you could even have this. Okay, but the key idea here is the number of relative extrema that you would have would never exceed 1 less than whatever your degree is. So now that we have all that, let's put it all together and let's start finding. Whoops, already kind of giving away some of the answers here. I want to take that away. Okay, let's put it all together and let's sketch some graphs now. So when we're sketching a polynomial function, I really break it down into 4 key steps. First, you want to find and graph any zeros that you have. Then you want to graph the end behavior. Then you want to graph the multitude of the zeros. And finally, you will need to plug in or plot a point between any zeros that you have. So let's try that with this function that we have here. So the first thing we're going to do is we're going to find the zeros. So we're going to set our function equal to 0. So 2x cubed minus 6x squared. And we're going to just solve this algebraically, factoring out a 2x squared. That's x minus 3. So our zeros are x is equal to 0. And we notice that that 0 appears twice. So we say that it has a multiplicity of 2. And then, and then 3 is the other 0. So we found our zeros, and now let's graph it. So we're going to have 1 0 at 0. And then we're going to have another 0 at 3. All right. Now the next thing is to look at our end behavior. We're on step 2. Well, let's look at the degree of our function, which is 3. So in other words, it is an odd degree function. Our leading coefficient is positive 2. Key idea here is that it's positive. So ask yourself now, what is the end behavior of this function? Well, as x approaches negative infinity, f of x is going to approach negative infinity. And as x approaches positive infinity, f of x is going to approach positive infinity. Don't worry too much about being really precise here at these endpoints. We just want to make sure that we understand the end behavior of our function. Now, the next step is to actually graph the multiplicity at each 0. So at 0, is our multiplicity even or odd? Well, it's even. Therefore, we're going to say that it's going to bounce off the function at that point. It's going to bounce off here. Now, we know that the graph has got to go down, and it has to come back up to hit the other 0 at 3. So when we're going to our 0 at 3, that multiplicity is odd, so it's going to cross through here, right? So we're just sketching a general idea of how it's behaving at that 0. Now, finally, I need to know what's happening in between these zeros. So one easy thing is just to plug in a point between those zeros. So I can just say f of 1, for example, try plugging in an easy number. When I plug in 1, I get 2 times 1 cubed minus 6 times 1 squared, and that's just equal to negative 4. So at 1, negative 4, I know it's going to hit that point. Now, do I know that it's going to go down even lower than that? Well, we won't really know the answer to that question until we get to calculus, where we can use our derivative to find relative extrema. For now, all I really care about is that you have a general sense of how that function is behaving in between the zeros. So we can just approximate it from there and then just kind of plug that in that way. So that would be an acceptable graph to give us a good sense of how this function is behaving at the zeros, at the ends, as x approaches positive and negative infinity. And that would be a pretty good graph. To finish off this lesson, let's try a problem where we're being asked to come up with our own function, pretty similar to how we started our lesson, but now we're going to actually graph it. So we want a function with a degree of 4 and 3 real zeros and a positive leading coefficient. So you can just try any zeros that you want. I'm going to just go ahead and do something like, let's say -2 is a 0, so x plus 2. Let's make another 0, x, and then let's make, or 0 I should say, so that means x is just our factor. And let's do something like, I don't know, let's make it really easy. Let's try something like positive 3. Okay, now notice it says 3 real zeros, but my degree has to be 4. Well, this tells us then that one of our zeros has to have a multiplicity greater than 1. So to make our life easy, let's just say that this 0 here, when x is equal to 0, has a multiplicity of 2. So there's our function. Now, let's go ahead and let's graph our function first. So if x plus 2 is a factor, that means -2 is a 0. 0 was another 0. And positive 3 was our other 0. And let's actually write this now in general form before we get too carried away. So let's say this is x squared. I'm going to multiply x plus 2 times x minus 3. So that's minus x minus 6 times x squared. So our function is x to the 4th minus x cubed minus 6x squared. So my degree is indeed 4. My leading coefficient is positive 1. So that means both ends of my graph need to be going up, since it's an even degree function. Going on to the multiplicity, I know that the only multiplicity that is even is at 0. So this graph is going to cross through here, it's going to cross through here, but it has to bounce off here because this is where I have even multiplicity. Now, how does it behave in between those zeros? Let's just plug in some points. Let's plug in -1, for example. When I plug in -1, I'm going to get positive 1 minus -1 minus 6 times positive 1. So that would just give me -4. So -1 gives me -4. So I'm just plug in something like this. Let's try plugging in positive 1 now. Should be something pretty similar. 1 minus 1 minus 6. So that's just going to give me -6. So 1, -6 is another point here. And again, it could continue to go on down, but I'm just going to graph it. I'm just sketching a graph, and that still tells me the behavior, and it still tells me the end behavior. All right. So hopefully this has helped you get a sense of how to graph a polynomial function, just reviewing the steps of wanting to make sure we graph the zeros and understanding the end behavior.